Okie dokie. Here's a lesson describing some questions on page 130 we have done concerning friction and net force. So, question 22 describes a block that slides along a rough surface and slows down with an acceleration of 1.25 meters per second. So, 1.25 meters per second squared. So I have indicated that the velocity would be in this direction, so the block is moving like this. It is slowing down, so the direction of the acceleration is backwards. When something is sliding along a surface and slowing down, it's easy to think that there is a force pushing it forward, but there is not. Okay? It is the block's momentum that keeps it moving forward. It is friction that slows it down. So the reality is that this is the net force acting on the object. Yes, gravity is pulling down and the floor is pushing up. Those two forces cancel out, leaving this as the net force. And so net force means the sum of all the forces acting on it. What is the actual force? What is the resultant force? Those are all ways of describing what net force means. So, we know the, what do we know? We're given the mass, and we're given the acceleration. Take a look at this. In this situation, the frictional force is the net force. And net force, when we write F equals ma, this is always net force. I'm going to write that in red because this is crucial. Net force. So when we write F equals ma, F is always net force. Always? Yep, always. So we can write the we can write the frictional force in terms of mu and the normal force, and because this is a flat surface, the normal force will be equal to the weight. Again, normal force pushes upwards, weight pulls downwards. They have equal amounts or magnitudes. So when we write it out like this, mu mg equals ma, the masses cancel. Fascinating. So that 1.4 kilograms that they gave us, we don't actually need that information. But you could plug it in anyway. Alright, so mu, I would divide both sides by g. And oops, wrote this the wrong way. This should be 1.25 over 9.8. And I put the negatives in there just because, well, gravity pulls downward and the acceleration is backward. But they do cancel out. Dividing gives us this. So this would be the coefficient of friction. Notice how there are no units. No units? Yep, no units. On coefficient of friction, it is simply a ratio. 23, you're helping your mom move a 41 kilogram bookcase, and you're pushing with a force of 65 newtons, and it is accelerating. So, notice how up here, the net force, there was only one force in the horizontal direction. That was the frictional force. This situation is different. There are two forces in the horizontal direction. You're pushing with a force of 65. Friction is pulling back or inhibiting that motion. The fact that it is accelerating means these two forces are not the same. If it were moving at constant velocity, then the sum of the forces would be 0. But it is not. It is accelerating, meaning there is some net force. Okay. So, what does that mean for us? It means, take a look at this. The net force, or the resultant force, okay, in the horizontal direction, is this minus this. Now, I put this one first because the fact that it's accelerating this way means the push is more than the friction. It's moving, okay, it's speeding up. So push minus friction is going to be the net or resultant force. For example, so this is a separate example, if you pushed with a force of 20 and friction pulled back with a force of 15, I'm hoping it's obvious that the result of those two forces would be 5 newtons to the right. Example. Okay, so that's what we're doing here. We also know that net force is equal to ma. Always? Yes, always. So we have mass, we have acceleration, we multiply 4.29 newtons is the net force. So I'm plugging that in to find the relationship between the push and the frictional force. So friction is less than the push, and it's less by an amount that is the net force. Once we know friction, plug in here, find the coefficient of friction, voila. Ooh, where are we going? Okay, next page. Alright, page 2, let's see. This is number 24. Looks good, looks good. So this is the hockey puck, where we're not given the mass of the hockey puck. So just like in that the number 22, it doesn't really matter. Here they test our ability to solve without knowing the mass. So it was given some initial velocity, we know the coefficient of friction, and we know that it stops after some distance. That's what we're looking for. So this is kind of right. Here, I did what I did before, where we know that in this case, because it was given some speed, it was given some speed and then is slowing down due to friction. While it is slowing down, there is one force that is the net force, and that is friction. Even though it's moving forward and slowing down, there is nothing pushing it forward. Okay, there is no force in the forward direction. It is only its momentum that carries it forward. So the frictional force will be the net force, which is ma. The normal force, because it is a flat surface, is mg. And look at this. The masses cancel. Mu g equals a. So for a flat surface where the only force acting on something is the frictional force slowing it down, we can say this. Okay, but don't just like write this formula down and just plug in for any old problem. It only applies to a specific situation, the one that I just described. So we find acceleration, and it looks like this. From acceleration, then we can use our old kinematics formulas to find the distance it goes. Here we go. This was our best friend there for a while. So final velocity squared equals initial velocity squared plus 2ad. Plug in, whoop, 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 and solve. Notice how acceleration is in the backwards direction. So the signs work out, and it goes this distance. All right. Next page. Alright, lastly but not leastly, haha, don't tell your English teachers that, we have the sort of similarities and differences between static and kinetic friction. So here's my Venn diagram. Both inhibit motion, meaning the frictional force will be opposite the direction of motion, or opposite the direction of the push. They also depend on the normal force. The greater the force pushing the two surfaces together, the greater the frictional force. Yet, static friction, the two surfaces are not moving relative to one another, and it will be greater than kinetic friction when the two surfaces are moving relative to one another. Question 28, here's the young kid at the wedding party and is sliding along the dance floor, doing his moves. The child has a mass of 25 kilograms. We're given that the coefficient of friction is this. We plug in, we find the frictional force. Easy. Oh, great.
Homecoming pictures are available in the office.
Okay, get your homecoming pictures. 29 is, so this is cards. So here's cards, and this fellow Derek is shuffling and dealing. So the card slides along the desk and comes to stop some distance away. Notice how the velocity would be in this direction and the acceleration would be in this direction, opposite directions because it is slowing down. Taking the mass whoops, no, taking the coefficient of friction and the mass and the acceleration due to gravity, plugging in, we can find the frictional force. Notice how this is just a card, okay, so it's a small force. And here, we were using the fact that this is a flat surface, so the normal force equals the weight, which equals mg. This is always true no matter what. This is only true for a flat surface. We will be getting into things sliding down inclined planes shortly. Now what do we do? Right. Net force equals ma. Always? Yes, always. And we know in this situation, because there's no force in the forward direction, it is only its momentum carrying it forward. The net force is the frictional force. Frictional force, net force, ma. We get an acceleration, and then like the previous problem a little while ago, we plug into our kinematics formula and solve for initial velocity. And note you're going to have to take the square root there as the last step. Okay.